but I want to give a brief introduction to Productivity East, which is a newly arrived hub for engineering, technology and management. Our vision is to work closely with local businesses and bring the world-class expertise of our 3 schools of engineering, computing science and the Norwich Business School to bear on practical problems, to explore new ideas and to develop innovative products and services. So I'd like to acknowledge the financial and moral support from the New Anglia Local Enterprise Partnership and the local sector groups like Tech East, who are co-sponsors of this event this evening, and the New Anglia Advanced Manufacturing and Engineering Group. The physical facility, Productivity East, is now open with lots of kit, a fairly unique collection of manufacturing technologies, including robotics. We've had lots of visitors already looking around the facility, and interested parties are welcome to contact us to have a look around. So just a reminder to all attendees to please mute and switch off their cameras. And I'll now hand over to Gerard to perform the formal introduction for tonight's speaker.
Thank you very much, Chris, and welcome everyone to this afternoon's presentation. Just to again welcome Professor Alan Norbury. Delighted that Alan has taken the time to join us and to give us his presentation today. As Chris has already alluded to, Alan is the Chief Technologist for Siemens Plc. He's Chief Technologist, but with a range of expertise, particularly in the Digital Industries division. And as you would know, Siemens is a global supplier of industrial plant and software manufacturing, automation and drive technologies, particularly in support of industrial customers across the UK and Ireland, and indeed more beyond across Europe and the rest of the world. Since 2011, Alan has worked closely with the high value manufacturing catapult centres. And as Chief Technologist, he dedicates a lot of his time in developing leading technology innovation to benefit Siemens UK manufacturing facilities and obviously Siemens industrial customers. Alan is a regular speaker at Industry 4.0 events and 4.0 plus, I might say. He's a visiting professor at the University of Nottingham and the University of Sunderland. He's a chartered engineer and the fellow of the Institute of Engineering and Technology, and also a fellow of the Institute of Innovation and Knowledge Exchange. He's a member of various boards, particularly linked to areas of support for advanced manufacturing, and is on the Liverpool City Regional Advanced Manufacturing Board for making it better. Alan, delighted that you could take the time to come and present to us today. Looking forward to your presentation. So over to you.
Thank you for that very, very kind introduction there, Gerard. I do appreciate that. I'm going to switch my camera off to make sure I get a decent bandwidth from home, and I'm going to share my slide. I'll make sure I switch on the volume as well so you can hear the videos, etc. So a little bit about my background. In addition to what Gerard's just said. So I started my career in 1978, so 43 years ago, man and boy, I worked for Siemens. I started as an apprentice, so I did ONC, HNC for 5 years, and then at the end of my apprenticeship, I then moved into low voltage control equipment, supporting well, things like push buttons, relays, contactors, circuit breakers, etc. I continued my studies, did a HND at Stockport College, and then eventually moved into automation. It was the early days of automation where a lot of our customers were a little bit frightened of it. You know, we talk about the fourth industrial revolution. There's been quite a lot of revolutions actually in my career span where people were a little bit frightened about technology, not quite sure whether it'd actually be as safe as the previous technology they were familiar with. And eventually, obviously, automation took over many manufacturing tasks in all different sectors. I moved to Germany for a while, looked after global accounts, one of which was Philip Morris. So I don't smoke myself, but the machines are really interesting, manufacturing 12,000 cigarettes a minute. And they actually sample the cigarette about 50 times throughout the length of it, look for the density, and if any of them are incorrect, they put it into a high-speed shift register and eject it further down the line. So that's where I really cut my teeth with high-speed counting and automation. Came back to the UK. I was a product specialist for fail-safe technology, hot standby technology, high-speed coding and positioning. And then I eventually set up a team from scratch, a team of application engineers. So these are technical consultants covering the UK and Ireland. I did that for 17 years, built up the team to have about 15 engineers working for me at one point. And then in parallel to that, in the last 7 years, I started working with the high value manufacturing catapult centres. They exist to accelerate innovation in the UK, to make the UK, let's say PLC, more globally competitive. And obviously a lot of our customers are also members, so it's a great way of reducing the cost and risk associated with innovations. So, and that's where I am today. So I'm going to move on to the first slide. And I make no apologies really for going back to the first principles of this thing called the Fourth Industrial Revolution. And it actually all started in Great Britain with the First Industrial Revolution. It should be actually Britain's Fourth Industrial Revolution. So it started with technology. So Arkwright spinning frame, Samuel Crompton's spinning mule meant that in the UK, we had the sort of centre of excellence for the mass production of cloth back in the 18th century. And that was all based on mortar and steam driven technology. The second industrial revolution was when we started to see mass production and conveyor systems. Apparently, the very first evidence of this was in the Cincinnati slaughterhouses back in 1870, a little bit before my time. You probably may have heard of the story behind the Model T Ford. You can have any colour you like as long as it's black. It was all about mass production of the same product. The third industrial revolution was when we started to see IT being used in manufacturing, and where we started to see more automation being used, and things like PLCs, which is where I cut my teeth in engineering, programmable logic controllers. Siemens' very first PLC was actually announced in the Paris Machine Tool Fair back in 1959. So we've actually been working in automation for many decades. The fourth industrial revolution has already started. And depending on the type of organization you are, you may be dabbling in digitalization, or you may be fighting against it, I don't know. And you'll see there that I put a bracket around the R. And the reason I've done that is because for most companies, it'll be an evolution. In other words, they are already manufacturing something and they are starting to introduce digitalization. And the technologies associated with Industry 4.0, you see on the right-hand side there. So virtual reality, augmented reality. So virtual reality, Siemens have now, I believe, 16 factories in the UK. We're quite diverse in what we do. And we are now adopting virtual tools to design our factories, to design our products, to design the layout of our production lines, and also ergonomics around how people assemble products, so that reduce the impact of repetitive strain injury, make sure that products are close to an individual to be able to assemble things. So we use virtual reality for almost everything now to make things secure and safe and accelerate those innovation cycles as fast as possible. Augmented reality means that now we can provide work instructions to our operators. Most people think of augmented reality as being those big glasses that you wear on your head for gaming. Well, actually, augmented reality can be in lots of different formats. So, for example, you could laser stream an instruction onto a work surface, so which wouldn't necessarily mean you have to wear the glasses. Digital twin, again, this is where you have the virtual version of something and a physical version. And the reason that we do that is, again, because when you're building something physically, and you make a mistake, it may take quite a while to change it, whereas virtually it's very, very easy to modify things very quickly. Cyber physical systems is where we're closing the loop on the digital twin. So we're starting to adopt the digital twin, and we're feeding data back in from the manufacturing process into the digital twin. Big data, many people have heard of the term big data, doesn't do a great deal unless you can actually harness that data, filter out the useless data, and turn it into what I call business data. And this is where more and more organizations are starting to develop smart algorithms to be able to make use of that big data. Internet of Things, there's more and more devices now, they're becoming smaller and smaller, more and more intelligent, that have the capability of connecting to the outside world onto Ethernet or the internet. Advanced robotics, and I don't mean the original perception of robotics in big cages. I'm also talking about here the cobotics, where we have robots supporting human beings, working alongside human beings. Cloud technology, this is partly around accessibility of data on a global scale. So you can compare machines around the world, for example. You can correlate data from different machines around the world or different processes or different factories. And you can have not just global cloud data, but you can have private cloud as well if you're concerned about security. 3D printing, many people may have heard of already. In business and manufacturing, we tend to refer to it as additive manufacturing. And this is actually changing the way we prototype products. What it allows you to do is develop very, very different piece parts. Because additive manufacture is based on layered technology, you can actually develop curvatures and cavities within a product, which you could not do in traditional ways of manufacturing. You can have components that may have several different parts. With additive manufacturing, you could do it with a single piece part. So having all these capabilities means you can look at the different heat transfer properties of these new design of products that may have curvatures within them. Cybersecurity is absolutely essential. If you think about the possibility of your machine being accessed from anywhere in the world, you have to ensure that security is absolutely key. So digitalization is changing all our lives. It changes the way that we stay informed. It changes the way that we travel. It changes the way that we buy things, but it's also changes the way that we manufacture products. And it's putting increasing pressures on manufacturers. How do we address this challenge of digitalization? But at the same time, it's also allowing companies large and small to change their business models based on the use of digitalization and data. So here's some examples which I'm sure you're all familiar with. When I was a young lad, we used to go down to a library if we wanted to read a book. Nowadays, you can download books onto your Kindles, onto your phones, onto iPads, etc. Again, when I was younger, if I wanted to listen to music, I'd go down to the record store and buy a vinyl record, whereas now you can stream music on almost any device. And on the bottom left-hand corner there, if you wanted somebody to help you with some DIY around the home, you wanted somebody to do the garden for you or install a bath or whatever, we used to go to the yellow pages. Whereas now you can actually go onto an app, you can get feedback from other people that have used that service, and you can also comment yourself afterwards if it's a good service or a bad service. And on the bottom right hand side, again, if I'm traveling in London or Scotland or Glasgow, I tend to use Uber nowadays. The great thing about it is you don't have to have cash. You can get receipts anywhere, either when you've booked it and also afterwards. And you can see where the taxi is, before the taxi arrives there, so you know how long to wait. And the point being here is these organisations that are developing these capabilities that change all our lives are mastering data. They are making use of data to develop new business models. Now, what are the drivers behind the fourth industrial revolution? Well, the drivers are you and I. It's an expectation for products to be available at our fingertips in a format that actually suits our individual needs. So the challenges for manufacturers are, well, how do we bring products to the market quicker than we've ever done before? If you just look at phones, for example, you get yourself a new phone, and then within a few weeks they brought out a new version of it. So how do you manufacture technology like that, where there's an expectation from customers for a new product to be available in such a short period of time? Flexibility. So again, there's an expectation for individuals that products are manufactured to their individual tastes. You just have to look at the automotive industry now. You expect to be able to specify almost everything on that car to suit your individual needs. And the amazing thing is that that car would be manufactured on the same production line as everybody else's customized car. In fact, there's a company in Germany called My Muesli, and you can go online and you can configure muesli to your individual taste. So you can add in nuts that you like, take out raisins if you don't like them, and they will deliver that product to your door to your individual taste. And that need for customization is covering all sectors today. Quality, again, there's an expectation for high quality. Again, back in the automotive industry, if you bought a car 30 years ago, 20, 30 years ago, you wouldn't necessarily expect it to run consistently without having to do something to it. Whereas now you expect those cars to continue running and then just book it in for regular service and that's it, forget about it. Efficiency, and I don't just mean energy efficiency, I think also resource efficiency. So making better use of your machinery. So if a machinery is capable of making one product, is it adaptable enough and flexible enough to make a different product on the same production line? And again, security plays an essential part in anybody's strategy around digitalization. So this is a model that Siemens use and adopt throughout our manufacturing processes. And it shows you the life cycle of manufacturing here. So on the left-hand side, we've got your product design, production planning, production engineering, production execution, and services. And this is what they call the product life cycle management. And all the way through that life cycle management, what tends to happen in most cases is you have different disparate sets of data that are not necessarily consistent throughout the life cycle of manufacturing. So what I'm showing here, if you get it right in the first place, so if you actually develop your 3D CAD for your production design, that data then can be reused in your production planning. It can be reused again in production engineering all the way through to services. And then what you can then do is develop what we call a digital twin. And that digital twin just doesn't apply to your product design. It applies all the way through the life cycle of manufacturing. While you're doing that, you're generating more and more data. That data can be harnessed and used by different types of third-party applications. And we use a platform called MindSphere, which is a cloud-based Internet of Things operating system, which allows you to securely manage that data and turn it into what I call business data. And I'll come back to that later on in the presentation. The other challenge that we have is that Siemens manufacture drives in Congleton, we manufacture drives in China, and we also manufacture drives in Germany. And from the customer's perspective, they want the same look and feel no matter where that product's been designed. And the way that we achieve that is by one set of the truth, one set of templates that are used globally. And we manage that through something called Teamcenter. And not only can that be used within our factories, but also it can be used throughout the supply chain as well, using this one existence of the truth. And this principle applies to all sectors. If you get it right, you can actually accelerate innovation cycles, you increase quality all the way through the life cycle of manufacturing in any sector. So what I've done here, so as I said before, I take a lot of my learnings from our factory in Congleton, where we manufacture variable speed drives for the world market. So what I'm going to show you here is a digital twin, how we apply it in our factory. So on the left-hand side there, we have the product design. So again, when our products are designed, we use 3D CAD for absolutely everything. One of the great things about that is you can share that with your supply chain. So in most companies' cases, most of their products are designed within the supply chain, and you basically end up assembling those components. Now, what we do is we digitally design the product, and then we can share that with our supply chain to make sure the product is manufacturable, because that's a massive challenge in today when you're going from prototypes to full production. Is that product designed for manufacturing? So the next level is, from that specification, then we build a virtual environment of the manufacturing process. And the reason we do it virtually, because you can move machines around very, very simply. You can include people, you can include factory layout, you can optimize the line, you can model absolutely everything. You can look at your attack rate of manufacturing by modeling the whole manufacturing process. And again, the data can be fed back into the product. If a product is quite difficult to manufacture, you can modify the product and then feed that back into the manufacturing process, closing the loop on the digital twin. Then we go to the real world, and again, it may not be quite perfect, so you can feed that data back into the virtual production environment, and then we continuously close the loop in the real world between the real world and the virtual world. And then finally, you have your product. And then when the product goes out in the real world, there may be, again, some tweaks or modifications that are needed. So then feed that back into the product design, into the production environment, whether that be real or virtual. And the idea of this closed loop is you're continuously improving your product, your manufacturing process, and all the energy, for example, and the resources that are needed for manufacturing. And I'll come back to that a little bit later when we show how we actually use this approach for building the ventilators during the ventilator challenge. So what could the future look like? And some people keep talking about now Industry 5.0. What does that really mean? Well, this is my version of it. So what you'll find is a lot of large manufacturers, tier one manufacturers, they rely heavily on their supply chain. Large percentages of manufacturers actually rely on supply chain. So what's the point of doing all this great innovation, digitalization in the tier one manufacturing if you don't include the supply chain? So what I've done here, I've turned it on its head. And if you can imagine this being a small company within a supply chain, and they're in manufacturing different types of widgets. And we're also trying to do that flexibly so we can achieve what we call mass customization to suit individuals' needs. So one of the visionaries behind the fourth industrial revolution was a guy called Dr. Siegfried Deyers from Bosch. And what he said would happen in the future is that raw material will contain the information within it for its manufacturing design, what part it would play in the supply chain, and also its own logistics. So it manages its whole manufacturing process and its logistics. So what I've done here, I've showed connectivity through a machine here in the tier one manufacturer, sending data through something we call an RFID tag. An RFID tag holds data. You can read and write to it without line of sight. So I've decided to use this technology here in this demonstration. Now, the benefit of putting all the information onto the RFID tag is that when the raw material goes into the manufacturing process, the product can tell the machine what to do to it, rather than the traditional way of manufacturing where the machine decides what to do to the product. The end result of that means every product can be a different shape, a different color, a different design. Now, the next step is it could potentially organize its own logistics. And all the time that product's going through the manufacturing process and being transported to the tier one manufacturer, that machine, if it's flexible enough in the tier one manufacturer, knows exactly when that product's going to arrive. And if there's a product building on the M25 or the M6 and it's not going to arrive there in time, if that machine's flexible enough, it could be adapted to actually do something else while it's waiting for that part. So this is kind of my vision towards this Industry 5 visualization. And the challenge is that a lot of supply chain companies are quite small, and to actually get to this stage of mass customization is a massive challenge. But other technologies around what we think Industry 5 could look like is around fully connected, fully adaptable supply chains, cognitive processes, self-adapting, self-healing machining. Quite often I think it would be human-centric. But what we won't see, I think, anymore is hand coding of PLCs, CNC machines anymore. I truly believe that actually coding will be done at a higher level. It will be done at a virtual level where we talked about the design of the manufacturing process and the product and also the machinery. And then that design will then filter all the way through to the PLCs and the CNC machines and the machines themselves to actually develop all the code for it. So I think engineering will take a very different view in the future. And the other thing as well, that actually, I think Industry 5.0 will actually be more around sustainability as well, making better use of resources, reducing energy consumption and optimizing productivity. Now, the other challenge is big data. And there's lots and lots of devices that are giving off big data. from things like wind turbines, trains, machines, different types of devices. And the challenge that we face is worldwide data volumes are doubling every year. So basically half of the data in the world that's been created in the last 12 months. So most of the data is not being used to its potential. And if you look at some of the predictions, they're saying by 2030, there'll be around 24 billion IoT connected devices around the world. And in terms of volumes of data, they're sort of predicting around 570 zettabytes of data. And you're probably wondering, what's a zettabyte? Well, a zettabyte is 10 to the power 21. And to put that into context, if you was to digitalize every word that's ever been said in every language since time began, that'd equate to about 42 zettabytes. So it's a lot of data. Now, what we're starting to see is organizations large and small developing apps that actually turn that data into business data. So things like energy consumption, it can identify faults on a machine, it can compare machines globally, it can look at energy efficiency and productivity. And the glue in the middle is what we use, is called MindSphere. And it can be based on various different cloud-based app platforms, whether that's Amazon AWS or different types of cloud-based platforms. So this is the way that we're managing data. We'll have artificial intelligence there, turning data into something useful. We have visualization through the apps. And this allows companies around the world to develop very, very different business models in industry. Now, the other challenge that we have is skills. And if you look at the picture on the left-hand side, there's a picture of me when I had hair in all the right places. And that was back in 1978. And these are the skills that I learned as an apprentice, traditional skills, foundation skills, which we still need to this day. But the challenge is we also need new skills. We need new skills to be able to work in the virtual environment. We need new skills to be able to manage all this data that's been flowing around the world. We need creativity skills to be able to work in the virtual environment. We need IT skills to be able to work in this virtual reality environment, and also something like gamification. So what's happening is now is a lot of the technology is being developed for gaming is also being used in industry. And if you look at the environments that I'm sort of working in there below, you know, with a large robot, you'd never be allowed to get that close to a working large robot without using virtual reality. And if you look on the left-hand side in the middle there, that's a Rolls-Royce Trent XWB engine. You can actually walk through the engine with it switched on, and you can see the heat transfer properties, you can see the airflow, and you can optimize that virtually before you build your physical machine. So it's changing the skills that we need going forward. So one of the examples of a great example of how we adopted this technology, and it made a massive difference to how we built up production of ventilators. So we'll just go on to the news story and I'll explain what part Siemens played in the ventilator challenge.
Some of the people who are recovering from the virus after being treated in intensive care will have been on ventilator machines to help them breathe. At the start of the outbreak, the UK government asked for businesses to make more of them to support more patients. Airbus is one of the manufacturers making key parts. And our reporter Brendan Williams has been to their factory in Flintshire to take a look.
It's a huge transformation, and it's happened at breakneck speed. Airbus staff at the Advanced Manufacturing Research Centre in Broughton were supposed to be designing aeroplane wings of the future. Instead, they're helping make machines to save thousands of lives in the here and now. When the UK government made a rallying cry for industry to build ventilators in the fight against COVID-19, engineering and technological companies stepped up. And today, the head of that consortium visited Broughton to hail an unprecedented effort.
In the face of a national crisis, to get that response from industry, no questions asked, everybody piling in, and this has just been incredible. I mean, you know, to see this degree of mobilisation and industrialisation in such a short space of time is quite incredible, really, and actually makes you feel proud to be British.
Creating an assembly line of this scale would normally take anything up to a year. This has been put together in less than 30 days, and although it's not yet running at full capacity, what you're seeing here is already remarkable. Following its
So that's just a quick introduction into what the challenge was. So basically, in a nutshell, the challenge was going from a company called Penlon, who built the ventilators originally, and they were their design and continue to do so today. They were building 10 ventilators a week, and what the government asked for was to ramp up production to hit the capacity of 3,000 units a week in a very, very short period of time. So this is what the ventilator looks like. Originally Siemens were only involved in one part of this with a flow meter, but when we actually proved what we could do digitally, we could actually ramp up production very quickly. Then we're also they gave us the opportunity to build the absorber part of the ventilator as well. So if you could look at what the challenge was on the left hand side there, this is how they manufactured ventilators at Penlon, 10 a week. And the kind of work instructions they had, bearing in mind these engineers were very, very familiar with ventilators. That's what they did day in, day out. And they had decades of experience in manufacturing them. And the kind of work instructions they would have would be things like hand tighten. Now we have to go from that situation where you had engineers that had all that experience over to engineers that basically had the experience of building aircraft. So they had never seen a ventilator before in their lives. And we also had to ramp up production from 10 a week to 3,000 a week. That was the challenge. And the way we started to do this was to design the layout. So the original thoughts were that we needed 90 cells to be able to assemble these ventilators. So within a 48-hour period, our team in Siemens Congleton, who are very, very familiar with using virtualization, that's what they do day in, day out in our own manufacturing, some of which are graduates, by the way. They actually virtually designed the whole manufacturing process. They simulated the whole line. They looked for any bottlenecks and removed them virtually. And when they did the calculation over that 48-hour period, knowing what the target was in terms of the tact rate, they actually said we only needed 30 cells. And when we went to manufacturing in the real world, they were bang on. It shows that the virtual tools really do work. We also had to accommodate social distancing. So again, we model that virtually to make sure that people weren't clashing, not getting too close to each other, to again ensure that we saved lives and people were safe in an environment that was COVID rife at the time. So I'm just going to pause it there. So this is one of the simulation tools that we use. Obviously, you have to identify all the different elements of manufacturing, which you can see there on that chart. But then we could also identify where the bottlenecks were, how often it had stopped, where it had failed, and remove those failures. So we could actually simulate the whole production environment, including the flow of the product and any potential faults. So here also we're generating work instructions. So if you, as I said before, the guys from Airbus were not familiar with ventilators, and we had to include obviously all the torque settings for all the nuts and bolts. They had to say exactly which nuts and bolts to use in what location, and where to find them as well in the assembly environment. So one of the other challenges, we had to manufacture jigs to ensure that we increase productivity and hold the components safe. When you're going at higher volumes, you have to optimize the environment of manufacturing. So on the left-hand side there, that is a typical type of code you would need for a CNC machine. But actually what they did was, from the 3D CAD drawing, they generated the code for the CNC machine without having to hand crank code in. And this is exactly what I was talking about before, where programming of units like CNC machines will go to a higher level in the future. So here you can see the introduction of humans as well. So one of the things we take very seriously in our factory in Congleton is the impact of humans. You know, when you got repetitive strain injury, potentially make sure they're not reaching too far, the impact it may have on their skeleton. So back injuries is always a problem, potentially. So in the past, we used to build these assembly stations in cardboard. It's tactile, you can see it, you can touch it. But now actually we've moved everything across to the virtual environment. So everything is done in what we call a virtual reality cave. So we invested in a virtual reality cave probably about 7 or 8 years ago. So a company called Vitalis built the cave, and we use that for everything now, for factory layout, for machine layout, for ergonomics with human beings, absolutely everything. And it means you get there a lot faster as well, and you can increase productivity by using these tools. So here, what we're showing is obviously the exponential growth of the manufacturing process for the ventilators. Obviously, initially it took a while to design the layout, and then you start to make your prototype or your initial versions of it. But the more you manufacture by closing the loop on the digital twin, you can actually increase productivity and manufacture more products. And we did prove virtually that we could actually assemble up to 3,000 a week. We got to a point where we'd actually made too many, so we only hit about 1,500, and then the government basically pulled the plug to say you've manufactured enough. So and it was a great example of how organisations, you see across the bottom there, with McLaren, with Airbus, with Ford, with GKN, all of those companies at the bottom working together as a seamless team. So all the egos went out through the window, and we just had to hit this target, and we achieved that. So if you look at that, you know, after 4 weeks from the cabinet office setting the challenge, 12 weeks later, we'd actually made over 11,000 ventilators. Without those digital tools, that never would have been achievable. So in summary, there's I think there's 3 things, maybe any takeaways that you'd like to take from the presentation. The first thing is infrastructure. So if you're looking to become a digital factory, then I asked the question of a lot of our customers: walk down your factory, look at all your machines, and ask yourself the question, how many of these machines have the capable of becoming part of the Internet of Things? In other words, does it have an Ethernet port on there? Can it connect wirelessly to your factory layout? And ultimately, that will enable you to connect into your office environment and then into your supply chain. And that could enable mass customization. Visualization. So are you making best use of virtual tools such as 3D CAD, modeling, simulation for designing your factories, your layout, your machines, your product, and also ergonomics with people? And last but not least is hybrid skills. So many youngsters now go through university and they have a focus on what they want to do, whether that's IT, whether that's engineering, whether that's gaming. Actually, what we're looking for today is people with hybrid skills. So that degree will get you to the interview, but after that, we're looking for people that are prepared to adapt outside their comfort zone, are prepared to learn learn new skills and work in different spaces than they're maybe trained up to work in. So, for example, our IT engineers, I call them engineers because that's what they are now, but the IT people in the past 10 or 11 years ago, they would work more in the office environment. Now they spend most of their time on the shop floor. Our engineers on the shop floor now actually work in virtual environments, so they have to have creativity skills very much similar to the gaming industry. So we're looking for people that are adaptable, flexible, and have hybrid skills. Well, why would we want to do that? The results could be that we have a capability of mass customization, potentially working towards batch sizes of 1. Well, why would you want to do that? Well, that meets the demands of consumers. If you mass customize a product to certain individuals' needs, they will pay more for that product. So we have this challenge that government are saying around productivity puzzle. Well, actually, you can increase productivity by increasing the value of your product. So you could have the same number of products and the same number of people and still increase productivity by adding value to your product through customization. Shorter time to market. The vision there is to get to 0 physical prototyping. So in our factory in Congleton, I'd say 10 years ago, we'd have 9 physical prototypes of a piece part, because the rest is done in the virtual world. Now we're down to about 2 or 3 physical prototypes, because we do everything in the virtual world, including engaging with our supply chain. And the vision is to get to zero physical prototyping. In other words, the first physical product we produce is our production unit. And last but not least, highly flexible manufacturing. So are machines capable of making more than one product, a different type of product? Are they flexible and adaptive enough to do that? That could be through robotics. It could be just through flexible environments and manufacturing. So those are the things, really, the takeaways. And the next slide is a great video, actually, where NASA used Siemens industrial software to virtualize and model and simulate the landing of rover on Mars. And if you think about it, it took 7 minutes from getting from the outer atmosphere of Mars to landing rover on Mars. It took 14 minutes for the information to come back to Earth. So by the time you got that information, it's too late. You can't do anything about it. And this is why zero physical prototyping for them was absolutely essential. It's called 7 minutes of terror.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. And we're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the Skycram maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
So I say, great example of zero physical prototyping. So digitalization, although that was rocket science, doesn't need to be rocket science. And if anybody there is listening is very interested in actually learning some of those tools around digitalization, things that I've been talking about today around Industry 4, Siemens have a number of online training courses that are free to register and free to actually progress through. So there's a link to Siemens training courses. Many thanks to everybody for your time, and if you've got any questions, now's the time to ask. Thank you.
Brilliant. Thank you so much. Thank you so much indeed, Alan. And fascinating talk. Lots of things to consider there. We do have some questions in the chat. So if I could maybe just step through them. Question from my colleague Ramez. And if you like, the question is, for digital twin are moving towards Industry 5.0. You have to deal with the real world sensors from multiple vendors with all the different configurations to harness their data. But sometimes there is a strict policy from giant companies to follow very specific communication protocols, components, products, and systems. So what is your opinion on this? And does interoperability impede companies' ability to innovate?
Very, very good question. It is a common problem for manufacturers, and what you tend to find is that most manufacturers will buy machinery based on the capability of machine without any consideration for communication. That's quite common, by the way. My answer to that would be, if you are a manufacturer and you're about to design a manufacturing production line, one of the first things you consider is specification. And one of those specifications should be the type of protocol, the backbone communication standards for industrial communications. And it needs to be an industrial standard, by the way. So we've adopted an open standard called Profinet. Not just Siemens, it's probably the biggest industrial communication standards in the world. So if you adopt an international standard like that, there's a very, very good chance that most of the products that you also buy for your machines will also have that capability of connecting. It's not always as simple as that, I know, but that's what you should do if you're building a brand new factory from scratch. There are lots of ways of connecting through different protocols, the Babel boxes and interfaces between one protocol to another. That's definitely doable. What we've done with our automation is we also have different modules for different protocols, so you can have it get a gateway through a PLC, for example, from Siemens. That's one way of addressing the challenge. So, for example, we have a field bus level called Profibus, and then we have the Ethernet level, enterprise level called Profinet, and through the PLC, you could actually communicate between those two gateways. We also do it with various other types of protocols as well. So it's doable, but the answer really is to get it right in the first place, and standardization is the answer to that.
And just maybe on the point of being able to innovate once you have hooked into all of these standards, does it impede innovation?
No, it would actually accelerate innovation, because it means it's easier to actually get data off machines. you could actually route into the machine either locally or remotely, so you can get more data. It minimizes downtime as well by the fact that you can actually navigate your way through routing into various different devices. And you can actually identify things are going to fail before they fail, by using condition monitoring, for example. So looking at the harmonics of vibration of a machine, you can tell when a bearing on a certain motor is going to fail before it fails. So there's lots of benefits of getting the standards right in the first place, definitely. But again, if there are different protocols involved, you can still do that to a certain degree as long as you've got the right gateways to do that.
Okay. Another question from Chris. Do you see the current focus on sustainability having an impact on consumer demand for product upgrades before end of life? And if so, how might that impact on product development cycle?
Funny enough, we had a chat about that before, didn't we, Gerard, about product design. So what we're looking at now at the moment, we manufacture variable speed drives in Congleton. We also manufacture motors. We're actually looking at investing in a project whereby we can evaluate how easy it is to disassemble our products using robotics. That might change the way we design our products in the future, because if products are difficult to disassemble with automation, then we may have to change the design such that it is easy to disassemble for reuse of material or resources, or recycle of material or resources. So I think sustainability will change the way we manufacture products in the future, and it won't be just Siemens. I think all companies will be doing that in the future. Also, the way we manufacture, we talked about sustainability early on in terms of the machinery and the efficiency of it. You're actually being more sustainable if your machine is actually capable of increasing productivity, because you're making more products with the same machine, therefore you're using less energy per product, so you're being more sustainable. There's lots of different ways of approaching sustainability. Everybody has their own different version of it, but it's quite complex if you look at the whole picture, including the supply chain as well. One thing we talked about earlier on is in our factory in Congleton, all our products come into the factory in cardboard boxes. And we thought, well, we have to spend time taking the cardboard boxes off, and we have to recycle the cardboard boxes. So we had an amnesty with these tote boxes that we brought back to Congleton. We put labels on their RFID tags, and we said to all our suppliers, can you put your products into those tote boxes rather than in cardboard boxes? And we've managed to do that. And we have RFID portals in our goods in bay. So when all these tote boxes are on top of each other, because you don't need line of sight for RFID, you can identify exactly what's been delivered, and then you can track it around the factory as well. So there's lots of different ways of looking at sustainability.
Excellent. Another question from Colin Darling. When discussing Industry 5.0, do you think that we are already witnessing mass customization? And furthermore, are there any other specific hallmarks which will allow us to identify the start of Industry 5.0?
I'd say, again, it's going to be an evolution rather than revolution. There'll be a gradual introduction of AI. There'll be a gradual introduction of machine learning. I think there'll be more focus maybe on human-centric manufacturing, such that the right level of information is provided to the user or the operator, rather than being bombarded with all the information that's available. And it depends on the skills of the individual. If somebody's working on a machine for the first time, then they want lots of information. If somebody's experienced and been working on it for 5 or 6 years, they want less information. You don't want to bombard people. And I think that's the way it will go in the future. I think the Industry 5.0 will be gradual. We're not there with 4.0 yet, by the way, with most manufacturers. And I'm a bit concerned about the hype around 5.0. I think we're too early yet, to be honest with you. But I was trying to show you my version of what it could look like in the future, especially with flexible supply chains. That's a real challenge to be able to achieve that across supply chains. But that's really the direction we should be going in, I think.
Okay, we have another question from James in the business school. We have been promised mass customization for a couple of decades. Every year I ask my students how many of them have custom genes, and I get the answer 0. Why is it different this time?
Well, I can give you a good example of how, again, I'm talking about Congleton again, how we've moved to mass customization. So Our drives traditionally, we had about 800 variations of a drive, and then we would ship them to Nuremberg, where we have a central warehouse, and all our products are shipped around the world from Nuremberg, which you can do with 800 variations. The latest drive that we have can have up to, and this is the latest figure I've heard, 70,000 variations. Now, if you can imagine you've got 70,000 variations, you can't really stock that many different variations. So now we have to take orders in our factory in Congleton and deliver to our customers around the world. So this is where digitalization is absolutely essential to be able to achieve that. And the relevant work instructions, because the operator will have a different product. Everyone that comes through is going to be slightly different. So you've got to increase quality as well by making sure the right work instructions there. It's got to be foolproof, and ways of closing the loop to make sure that if they pick the wrong nut or the wrong washer off the bin bins, that it actually warns you and tells you that. So yeah, mass customization is already happening. Not in all companies, but it's definitely happening, and there's definitely an expectation from consumers for mass customization.
Okay. Fabian has another question. With digitization and how the future is to have everything connected to the internet, how big is the cybersecurity risk that is faced by industries?
Well, in the past we have had challenges around cybersecurity, and the more people that actually get involved with it, and again, standards are really important as well around cybersecurity. The one thing that worries me is those cheap and cheerful solutions that are very, very low cost to implement, but have no consideration for cybersecurity. Whether that be password level, whether that be individual recognition from the individual, or limitation of what's accessible. You might want to be able to enable people to view data but not modify data. There's lots of different levels of cybersecurity, and that's definitely possible with Siemens automation. There used to be a key switch that we had on the front where you can actually set it to a mode where you can read and write or read only. Well, that doesn't work anymore, obviously. So you need to do it in different ways. And it was funny enough, it was when I used to get involved with presses, big, massive rotating presses. And the operators used to find ways of getting over the safety switches by using the feet and the hands in different positions. Well, when they moved away from that to safety PLCs, although everybody was frightened of it, actually it was safer because they couldn't do that anymore.
Yeah.
And there's always a fright, that black box there is going to be very unsafe. But no, in reality, it was safer.
The human in the loop will always find a way. Another question from Yogesh. Can we build cyber physical systems for the existing traditional manufacturing facilities? And what can be the motivation for them other than probable increase in productivity?
Brilliant question. And the answer is yes. So I do a lot of work with the catapult centres. The Advanced Manufacturing Research Centre in Sheffield, they've actually got an old lathe, I think it's a Bantam lathe. There's no sensors on there whatsoever. You might have a switch to switch it on and switch it off, and that's about it. What they've done is they put sensors all over it. Again, vibration. Through vibration, you can tell if the motor's going to fail before it fails or a bearing's going to fail. That increases productivity, of course. You can identify information through temperature changes. You can identify potential failings on the products that you're working on by vibration and temperature. So actually, all these sensors on older machines does make sense. You just have to make the right calculation. So what they've done, they've gone over the top. They put more sensors than you really need to, which you can do in a research environment. But the idea is then you bring it back to what are the essential sensors that you really need to be able to optimize the manufacturing process, increase productivity. So the answer is yes, you can do it. It doesn't have to be expensive either, by the way, to do that. And
I suppose, just since I'm a telecoms engineer by background, a lot of what you've said about digitalization and digital transformation, for me, it's network enabled digital transformation, because without the network, you're talking about standalone islands, in which case you may be able to reinforce the cyber bit, but all of this data that you talk about in this interconnected supply chain becomes a challenge. So my question is, to what extent do you rely on having a network that's trusted, behaving itself, always available, and how does Siemens join that part of the jigsaw into a solution you give to your clients?
Well, in terms of availability, what we do on the physical Ethernet, so this is your real copper piece of wire, is you tend to have redundant systems. So you have a circular system, and then you have a switch in there. So if a cable is broken at one point, it switches over to the other half. So redundancy is quite common, really. And you can also do that with the PLCs. You can have redundant PLCs as well. If it's wireless, believe it or not, you can have redundancy in wireless. You can have two different frequencies. I'd highly recommend that you don't use domestic wireless access points in industry. There are industrial access points that are very, very robust, where you can have dual frequency. You can have managed switches, so it can tell you if there's a potential failure. You can actually analyze the environment to make sure you're getting the best wireless communications throughout the whole factory. And now we're moving towards 5G and Wi-Fi 6. I think that's going to be absolutely essential that you have those diagnostics and management capabilities. There'll be a bit of a fight between 5G and Wi-Fi 6, which one is a little bit like your Betamax and VHS, I think, as to who's going to win the lead. You may end up with both possibly. But yeah, Siemens are developing technology for both types of, let's say, views on industrial communications. And again, safety. You can actually have safety communications over copper or wireless, because the safety was in the protocol, not necessarily in the medium. So if you lose connection, basically the fail-safe position is to go to zero. As long as you're aware of that, then it can be as safe as houses.
Well, Alan, I think we have hit our time, and that's been fascinating. And I just want to thank colleagues for putting the questions in the chat. But more importantly, Alan, I want to thank you for a fascinating presentation. And normally we would be applauding from a distance or face to face, and we'd be going straight now for a pizza and a beer, perhaps. But hopefully next time we'll do that. So on behalf of Chris and other colleagues in Productivity East, huge applause for your time and for really articulating some of the challenges that we have to face. And so I'll hand back to Chris.
Thanks, Gerard.
Great. Yeah. Likewise, thank you, Alan, and thanks to all attendees. We will eventually put this on YouTube, and it'll be on the Productivity East website. But again, just to echo Gerard's thanks to you, Alan. If you can hang about, I don't know whether you've got to shoot off, if you can hang about for a couple of moments at the end, because what you're saying about the Penlon ventilators is topical for me. Thanks to all attendees, and I hope you enjoyed the seminar, and keep watching this space for more information on Productivity East and the research and innovation agenda. Thank you all very much.
Thank you, everyone.